before we get to our last example, or the example I'm real excited about, I do want to talk very briefly about about objects that roll and slip. And we talked about this before, slipping and skidding. Okay. When an object rolls without slipping, in other words, for what we would call a smoothly rolling object. What that means, and this goes back to what we did when we first started talking about angular motion, rotational motion. What this means for a smoothly rolling object is that the linear acceleration is equal to r times the angular acceleration. And I'll even write that out for you. Linear acceleration equals r, the radius, multiplied by the angular acceleration. Now, earlier I just gave you this as, this is just fact, this is the way it is. The linear acceleration equals r times the angular acceleration. Turns out that is only the case if an object is smoothly rolling. Okay, if we're talking about rolling, this is only true if the object is smoothly rolling, much like this softball, okay? It's rolling smoothly, it's not slipping, it's not skidding along the surface. If something else happens, let's say for instance, if there is, I guess what I'd say, not enough friction, that means the object will slip or spin too much, okay? Let's say there's not enough friction to cause enough, to cause it to like grip. What that means is every once in a while the object will spin a little bit too much. It'll rotate more than it actually translates, okay? If this happens, again, this is like your tires spinning when you're trying to pull away from a stop sign a little too quickly. This means the object doesn't really move anywhere. It starts rotating more than it translates. Which leads to our conclusion that if this happens, if the object spins more than it really translates, I guess is the best way to put it, that means the linear acceleration is less than the product of the angular acceleration times the radius. What that means is the object is rotating more. It has a bigger angular acceleration than its linear acceleration. Kind of makes sense. There's another case. What if there is too high of a linear speed? You might get a case where an object is moving so fast that it does rotate a little bit, but it's also skidding at the same time. Skids or slides. And the condition for that is, well, the opposite. The linear acceleration is greater than the product of r and alpha. Now I'm going to make a note with this. There's a couple things in this topic, in this unit, that I think makes sense, but I'm also not really 100% sold on the explanation. This is one of them. This makes good enough sense to me, but I'm just going to let you know that I'm not 100% sold on this as like this being 100% correct all the time. Okay? I encourage you, if you want, come up with your own explanations, look things up, see if this is right. This seems to make sense to me. I definitely could be missing part of it. Okay, I definitely could be missing some sort of key concept. If I am, if you're interested, please do look this up. But I'm pretty sure, and this isn't a huge part of the unit anyway, so I'm pretty sure this is fairly accurate. But I do encourage you to, check me on that. Let's go to the back. Let's get into an example that I can almost guarantee you'll see at some point on the AP exam. Because they've asked many similar questions over the years. And it's an interesting question, okay? we dealt a lot, even in Regents physics, we dealt with objects that were on ramps. We dealt with objects, mainly sliding down ramps though. Okay, that was the focus of what we were doing, objects sliding down ramps. What we're going to look at now is an object that rolls down a ramp instead. And again, this is going to be one that's pretty writing intense, so I'm going to back up a little bit so I can make sure I have enough room. One more. Okay. This one is going to be, there will be a lot that we write down here. So an object rolling on a ramp. And let's make our object a sphere rolling down a ramp, just for the fun of it. Sphere rolling down ramp. Now the first question is, how do you know it rolls? What would make it roll? Why wouldn't it just slide down the ramp? If it were sliding down the ramp, what that would mean is there is not enough friction to make it roll. It would mean actually that it's completely frictionless. Okay? It would mean that there's nothing to cause any sort of rotation. So it rolls because there must be friction. Otherwise, it would slide. Okay? So something rolling, if something's rolling, that is a dead giveaway that the surface between them is not frictionless. And we're going to go with the condition that the rolling is smooth. The point of friction, the point of contact right here, we're going to go with the idea that that is momentarily motionless as it rolls. What this means essentially is that static friction is acting on our object. So we need a free body diagram. And since it's an object that is rotating, we need to draw our free body diagram and need to show exactly where all the forces are acting on the object. So, here are the forces acting on our sphere. Obviously, there's a force of gravity. It acts from the center of mass of the sphere. This is a normal sphere. Center of mass is right in the middle. Okay? Fg. I guess we should have an axis, first of all, and we should label this sphere. Our axis down the ramp, like this. And I suppose we should say that the clockwise torques, I know I keep doing this, where I tell you all the time, like counterclockwise is positive, all three examples we've done so far, clockwise has been positive. But if x is positive and y is positive, it looks like this is going to have to be positive as well. So this is a positive torque. We need to split up Fg into components. So we have one component that points perpendicular to the ramp, one that points parallel to the ramp. Here's our ramp angle. Should probably draw that in here. So this is Fg cos theta, Fg sine theta. Now this is a sphere on a ramp. It's on a ramp surface, so we know that there must be a normal force acting on it. Normal force acts from the point of contact up like this. Okay? By the way, the axis of rotation for the sphere is right here at the center of the sphere. It's rotating about its center. Okay? Let's see here, what else? We also know that there must be a force of friction. The force of friction will act at the contact point between the sphere and the ramp surface. And, again, let's imagine what would happen if there was no friction. If there was no friction, this sphere would just slide down the ramp. This point on the bottom of the sphere relative to the ramp would move to the right. That means, since there is friction, the force of friction must point back to the left. Okay? That's different than last time. Okay? That's different from the car tire example before. It's all situationally dependent. The car tire, something else is making it rotate. Okay? Here, gravity, well, here it's not the force of friction that causes it to rotate. It is the force of friction that causes rotation. It is opposing the motion of the sphere down the ramp. But before, it was something else. The motor was causing a torque that caused the tires to rotate. Friction was just what allowed the car to get propelled forward. Like I said, friction is very tricky. Here's our free body diagram. Out of all these forces, only one of them causes a torque. Only the force of friction will actually cause a torque. The other forces. Well, let's take a look. We've got components, they don't really count. The force of gravity, that acts right at the center, or at the axis of rotation. Its sphere is rotating about its center. So the other forces here act either at our axis of rotation, which is at the center of the sphere, or the normal force doesn't act at the center of the sphere, but if you look, it's on a line parallel to the line between the axis of rotation and what I'll call the point of application, where the normal force is applied. Back when we talked about all the different ways to calculate torque, one of the ways that we said was to find the line of action. It's basically you take the direction of the force and you make a big imaginary line. Well, this line of action happens to pass right through the axis of rotation. What that effectively does is, you can look at it one of two ways. It either makes r perpendicular 0, or it makes it so that sine theta, r is this way, the force is this way. They are 180 degrees apart from each other because they're in opposite directions. The sine of 180 is 0. Okay? The normal force and the force of gravity cause no torque whatsoever. The only torque comes from the force of friction. That is what causes the rotation, the force of friction. What we need to do now is not only, just like in our last little mini topic, we need a net force equations and we need net torque equations. Let's start in the x direction. This will be very similar to what you've always done. F net x equals, well, we have the component of the force of gravity, Fg sine theta. This force is also in the x direction, minus the force of friction, equals m ax. By the way, this is static friction, okay? This object is not sliding down the ramp. This is static friction. So we need to be careful here. If this is static friction, we don't know that this is the maximum possible force of static friction. Unknown if this is FF max. It could be, it could not be. We don't know. Okay? We'll talk about that case in a little bit, if it in fact is. Okay, let's go on to the F net in the y direction. Very standard. We have normal force minus Fg cosine theta. We know that's equal to ma(y). We know this object is not accelerating perpendicular to the ramp. This must be 0. We get Fn equals mg cos theta. There's our net forces in the two directions. Now we just need the net torque. There is only one torque. It is a torque from the force of friction, and it is equal to I alpha. Now we haven't talked about a couple of these things yet. We have not talked about the rotational inertia of the sphere. The equation for rotational inertia of a sphere is as follows. Remember, it has to have the coefficient. The coefficient for a sphere is 2/5 mr squared, where r is the radius of the sphere. We could plug that right in. Matter of fact, let's do so. Let's say, let's see here. Okay, so this is r ff times ff times sine theta ff equals 2/5 mr squared. And remember our little equation for alpha, we know that linear acceleration equals r alpha. Therefore, alpha must equal a over r. Okay. We look back at our free body diagram. The force of friction acts one radius, the radius of the sphere, away from the axis of rotation. That's r. Uh-oh, we don't know what the force of friction is. We can't say mu Fn because we don't know if this is the maximum force of friction. Thankfully, we could say something else. Why don't we rearrange this and solve for the force of friction? We bring this over to the other side, we bring the max over, and what we end up with is that the force of friction is equal to mg sine theta minus max. mg sine theta minus max. And then this sine theta for the force of friction, remember, here's r, here's f, they are perpendicular. This sine theta goes away. This one, however, does not. This is not the same theta as this. You have to understand what every single theta means. This is the theta between r and f. This theta comes from our free body diagram. It is the angle that the ramp makes. I'll continue writing. 2/5 m r squared. This acceleration, okay, this linear acceleration is really the acceleration down the ramp. Oh, I guess I should write r for the radius of the sphere. Okay, this is ax, and this is r. So what I've done here is m is obviously the mass of the sphere. Capital R is the radius of the sphere. If you look, it's very similar to what we were doing yesterday. I have an m in every single term. Cancel, cancel, cancel. I have, let's see, r squared will cancel out with r, and I have an r in both terms. The r's will completely go away. Here's what I'm left with. G sine theta minus ax equals 2/5 ax. If we are solving for the acceleration, I add this over to the other side. What I end up with is g sine theta equals 7/5 ax. Therefore, the acceleration of this object down the ramp ends up being 5/7 g sine theta. 5/7 g sine theta.